He's sitting in a folding chair 20 meters from a fully fueled ballistic missile. Marshal Mitrofan Nedolin knows the rocket is leaking. He can see the engineers working beneath it with hand tools, their backs bent under 140 tons of hypergolic fuel, the kind that burns skin on contact and ignites the moment it meets air. He knows the ignition circuit is still live, and he refuses to move. Not because he's brave, because 3 weeks ago, someone in Moscow set a deadline, and in the Soviet Union of 1960, missing a deadline is more dangerous than sitting next to a bomb. Around him, 126 men are troubleshooting a missile that has never successfully launched. Nobody suggests evacuation. Nobody steps back. The fear of what happens if they fail is stronger than the fear of what's hanging over their heads. Nedolin checks his watch. What he doesn't know is that 40 seconds ago, their repair attempt sent a signal into the fuel tanks. Something inside the rocket has woken up. The system thinks it's time to launch. The engineers hear a click. Then the air turns to fire. Site 41 at Baikonur Cosmodrome. The R-16 stands 34 meters tall, a white cylinder against the October sky. It is the Soviet Union's first operational intercontinental ballistic missile, designed to reach targets in the United States in under 30 minutes. 2 stages, hypergolic propellants in each. The fuel is unsymmetrical dimethylhydrazine, a clear liquid that smells like ammonia. The oxidizer is nitrogen tetroxide, rust-colored and corrosive. When the two meet, they ignite instantly, no ignition system required. That chemistry gives the R-16 its edge. It can launch within minutes of an order, unlike kerosene rockets that need careful countdowns. But it also means the rocket is a bomb the moment both tanks are full. Standard procedure calls for the pad to be evacuated during fueling. Everyone withdraws to bunkers 200 meters away. Propellant transfer is monitored remotely. If a leak appears, technicians do not approach until the tanks are purged and vented. But today, October 24th, that protocol has been suspended. The fueling is complete, yet engineers remain at the base of the rocket, running diagnostics on the second stage ignition circuit. The umbilical lines are still connected. Marshal Nedolin has ordered the work to proceed on site. He wants to see the fault diagnosed in person, not through reports radioed from a distant bunker. So the evacuation never happens. The 200-meter safety perimeter collapses to zero. The engineers trace voltage through connectors buried deep in the rocket's second stage. They are looking for an intermittent fault, a signal that appears and disappears without pattern. The ignition circuit is still energized. It has to be, or they cannot see the fault when it occurs. Multimeters click. Oscilloscopes sketch voltage curves on glowing screens. One technician lies on his back beneath the engine bell, reaching up into the nozzle throat with a probe. Another stands on a scaffold, elbow deep in a cable bundle. They work quickly because they know the clock is running. 14 days until November 7th. 14 days to fix a problem that would normally require weeks of testing in a safe hangar, far from any propellant. Nikita Khrushchev wants a successful R-16 test before the Revolution Day parade. The deadline is not negotiable. The Soviet leadership has promised the world a new intercontinental missile, proof that the motherland can strike American cities from Soviet soil. A delay means embarrassment on the world stage. For Nedolin, it means something more personal. He commands the strategic rocket forces. The R-16 is his program. If it fails, if it misses the deadline, the blame will land on him. In Soviet command culture under Khrushchev, that kind of failure ends careers. Sometimes it ends freedom. So Nedolin calculates. The engineers are competent. The fault is probably minor. A loose connector, a bit of contamination. If they can find it today, the rocket flies tomorrow, and everyone goes home a hero. The electrical fault is intermittent. Signal noise in the second stage igniter circuit. Voltage appears when it should not, then vanishes. The engineers suspect a short, possibly in a connector deep inside the rocket structure, where vibration during fueling could have loosened a pin. Or contamination, a bit of propellant vapor condensing on a circuit board. To diagnose it, they need the system live and the propellant loaded, because the fault only appears under full electrical and mechanical load. There is no way to simulate that condition in a lab. So the choice is binary. Leave the rocket fueled and find the fault now, or drain the tanks and lose 2 days. Nedelin does not have 2 days. The R-16 has no remote shutdown. Once the ignition sequence begins, the only way to stop it is to physically disconnect the umbilicals at the pad. There is no button in the bunker that can kill power to the igniters. The design assumes the pad will be empty when the engines fire. If something goes wrong during a countdown, the crew is supposed to run. But today, the crew is still there. The ignition circuit is live. If a signal reaches the second stage igniter, whether by accident or malfunction, the engine will fire. And because the rocket is fully assembled, that exhaust will punch straight down into the first stage fuel tanks. There is no abort. There is no safety margin. There is only the assumption that nothing will go wrong in the next few hours. Draining the R-16 requires 48 hours. The propellant must be pumped back into storage bunkers, not simply vented. Hypergolic fuel cannot be dumped on the ground. It ignites on contact with organic material and releases toxic fumes. The tanks must be purged with inert gas, then inspected for residue. The entire process demands careful sequencing, and it cannot be rushed. Nedelin looks at the calendar. 48 hours puts him at October 26th. Add a day to diagnose the fault safely in a hangar, another day to reassemble and refuel. That brings him to October 29th. Then he needs a weather window, a tracking station window, and final checks. The math does not work. He will miss November 7th. So he makes the decision. The tanks stay full. The engineers stay on the pad. In the Soviet military of 1960, missing a deadline set by the Kremlin is not a technical failure. It is a political crime. Commanders who disappoint Khrushchev find themselves reassigned to remote garrisons or quietly arrested. The memory of Stalin's purges is only 7 years old. Nedelin knows the cost of failure. So do the engineers. Nobody suggests halting the work. Nobody argues for the 2-day delay. The fear of what happens if they fail to meet the deadline is stronger than the fear of working beneath a fueled rocket. That calculus shapes every decision on the pad. Safety protocols exist, but they are written for peacetime. This is not peacetime. This is a Cold War deadline, and the consequences of missing it are immediate and personal. 1845, October 24th. The engineers are still tracing the fault. One technician adjusts a voltmeter lead inside a cable bundle near the second stage igniter. The circuit is live. He is careful. But somewhere in the tangle of connectors and relays, a signal finds a path it should not take. A short, or a test pulse sent from the wrong console. Nobody will ever know for certain. What matters is that the second stage igniter receives a command. The system thinks it is time to launch. The pyrotechnic charge fires. The igniter sparks. Hypergolic fuel and oxidizer meet in the combustion chamber. And the second stage engine, still mated to the first stage, still sitting on the pad, ignites at full thrust. The second stage engine fires at full thrust while still attached to the first stage. A column of exhaust punches downward, not into open air, but into the rocket's own structure. The combustion chamber is designed to vent upward during flight. On the pad, the exhaust has nowhere to go except through the interstage section and into the first stage fuel tanks below. The temperature is 3,000 degrees Celsius. The aluminum structure begins to melt immediately. The first stage tanks hold 140 tons of propellant under pressure. The thermal shock ruptures the tank walls. Fuel and oxidizer, kept separate by millimeters of metal, pour into the same space. They meet. Hypergolic ignition is instantaneous. 140 tons of hypergolic propellant ignite in less than 2 seconds. The pad becomes a combustion chamber. The fireball expands radially outward, contained briefly by the launch scaffold, then erupts in every direction. The pressure wave travels faster than anyone can run. The thermal pulse travels faster than anyone can react. Nedelin is still sitting. The engineers are still standing. They have no time to turn, no time to take a step. The temperature at the center of the fireball exceeds 3,000 degrees Celsius. At that heat, human tissue does not burn, it vaporizes. Clothing ignites before the pressure wave arrives. Skin carbonizes in under 1 second of exposure. By the time anyone realizes what is happening, it is already over. Hypergolic propellants ignite on molecular contact. No spark plug, no ignition delay, no countdown. The R-16 uses unsymmetrical dimethylhydrazine as fuel and nitrogen tetroxide as oxidizer. When the two liquids meet, a chemical reaction begins in microseconds. The fuel donates electrons. The oxidizer accepts them. Energy is released instantly as heat and expanding gas. The reaction is exothermic, meaning it produces more heat than it consumes. That heat accelerates the reaction, which produces more heat in a runaway cascade. Within milliseconds, the combustion temperature reaches 3,000 degrees Celsius. That is hot enough to melt steel, vaporize aluminum, and carbonize human tissue in under 1 second. The chemistry does not wait. It does not need permission. It simply happens. At 3,000 degrees Celsius, materials do not simply burn, they change state. Aluminum, which melts at 660 degrees, turns to liquid and then vapor. Human tissue, mostly water and carbon, carbonizes. The water flashes to steam. The carbon remains as ash, fused to whatever surface it touched. The process takes less than 1 second for anyone within 30 meters of the fireball center. The thermal pulse travels at the speed of light. People experience flash burns and ignited clothing before the pressure wave physically reaches them. By the time the blast wave arrives, carrying hot gas and debris, the thermal damage is already complete. There is no gradual escalation. The heat does not build. It simply appears, full intensity, faster than nerve signals can travel to the brain. The launch pad acts as a combustion chamber for the first fraction of a second. The scaffold structure, designed to support the rocket, briefly contains the fireball. Then, the pressure exceeds the strength of the steel beams. The structure fails. The fireball erupts radially outward in all directions. The pad geometry funnels the explosion. Workers at the base of the rocket are in a bowl-shaped depression, with the scaffold forming walls on 3 sides. The single exit is a ladder on the perimeter, 15 meters from the rocket base. At a fireball expansion rate of 50 meters per second, the flame front reaches the ladder in 0.3 of a second. No one inside the pad area can run 15 meters in 0.3 of a second. The geometry ensures maximum casualties. The inner 50-meter radius is the kill zone. Anyone within that distance receives a lethal thermal dose before the pressure wave arrives. Clothing ignites. Exposed skin burns through all layers. Lungs inhale superheated air, which causes immediate internal burns. Death occurs within seconds, either from shock or from respiratory failure. Beyond 50 meters, the thermal intensity drops. People still suffer burns, but they have seconds to react. Some run, some drop to the ground, some shelter behind equipment. Survivors are concentrated in the blast shadow of concrete bunkers or outside the initial radius. The line between life and death is sharp. Inside 50 meters, no one survives. Outside, some do. The physics is binary. The outcome is binary. Human reaction time is roughly 0.2 of a second. That is the time from stimulus to muscle movement. The thermal pulse arrives at the speed of light. The fireball expansion is subsonic, but still faster than running speed. Even if someone at the pad base sees the ignition flash and begins to move instantly, they cannot cover 15 meters before the fireball reaches them. The mathematics of escape are unforgiving. Distance divided by speed equals time. 15 meters divided by 5 meters per second, a fast sprint, equals 3 seconds. The The fireball covers the same distance in 0.3 of a second. There is no scenario in which anyone within the inner pad area escapes on foot. The only survivors are those who were already outside the radius when the ignition occurred. Personnel stationed 200 meters away see the flash. Some begin running toward the pad. Then, the secondary tanks detonate. The first stage oxidizer tank, ruptured but not fully consumed, explodes 15 seconds after the initial fireball. Then the second stage tanks. Each detonation sends shrapnel and burning propellant outward in a new radius. The rescuers stop. They turn back. Radio calls from the bunker confirm what everyone can see. No movement on the pad. No survivors visible in the immediate area. The scaffold has collapsed into burning wreckage. Flames and toxic fumes blanket the site. There is nothing to rescue. Only bodies to recover once the fires burn out. Fire suppression crews cannot approach for 20 minutes. The propellant fires are still burning. Nitrogen tetroxide, the oxidizer, releases nitrogen dioxide fumes when it burns. The gas is rust-colored and toxic. Inhalation causes pulmonary edema, fluid in the lungs. The crews wait for the wind to shift, for the fumes to disperse. They wear respirators and protective suits, but the heat is still too intense. The aluminum scaffold is burning. Aluminum fires reach temperatures high enough to reignite even after water is applied. So they wait. At 18 minutes past the explosion, the wind shifts. The fumes clear enough for crews to approach. They move in with foam and inert gas. The fires are suppressed by 1910 local time. Then, the recovery begins. The recovery crews reach the pad at 1915. The scaffold has collapsed. Twisted steel beams lie across the concrete foundation. The rocket is gone, vaporized or scattered as fragments. What remains are shadows, carbon stains on concrete where bodies fell, fused metal fragments that were once tools or equipment, and remains. Within the inner 30 meters, there are no intact bodies. The thermal pulse and sustained fire have carbonized soft tissue completely. What the crews find are fragments, bones, teeth, material fused to metal surfaces. Outside 30 meters, in the blast shadow of equipment or bunkers, some bodies are recognizable, but most are not. Identification will require forensic protocol, dental records, personal effects, anything that survived the heat. Forensic teams work for 3 days. Soft tissue is destroyed. Dental records are unavailable for most personnel. The Soviet military did not maintain comprehensive dental archives in 1960, so the teams rely on what survives extreme heat. Military medals, which are made of high melting point alloys, belt buckles, uniform insignia, watches, anything metal or ceramic that can be traced to a specific person. Each fragment is photographed, cataloged, and cross-referenced against personnel rosters. Families are contacted. They provide descriptions of what their husbands or sons wore. A specific medal, a wedding ring, a watch model. Slowly, identities are confirmed. Some remains are matched to names, others are not. Those go into a common grave, unidentified. On October 25th, one day after the explosion, the Soviet government classifies the disaster. No public announcement, no press release. Internal military reports refer to it only as an accident, with no details. Families receive closed casket funerals. Death certificates list no cause of death, only dates. Marshal Nedelin is reported to have died in a plane crash. The other casualties are listed as training accidents or unspecified incidents. Nobody outside the strategic rocket forces is told what happened. Even within the military, information is restricted. Personnel at Baikonur are required to sign secrecy oaths. Violation means prosecution. The disaster is erased from official history before the bodies are buried. Nikita Khrushchev personally orders the information blackout. His reasoning is strategic. The R-16 program is central to Soviet nuclear deterrence. Any public admission of a catastrophic failure undermines the credibility of the Soviet missile force. The United States must believe that the Soviet Union can launch intercontinental ballistic missiles reliably. A disaster that kills over 100 engineers, and the commander of the Strategic Rocket Forces suggests otherwise. So the disaster is hidden. Internal military safety reviews are conducted, but the findings are never published. Families are told nothing. The November 7th parade proceeds on schedule, with no mention of the October tragedy. The Soviet Union projects strength while burying its dead in silence. An internal investigation is conducted by the Strategic Rocket Forces. But here's what makes this truly chilling. They know exactly what went wrong. A premature ignition signal in the second stage igniter circuit. A short circuit or botched test procedure. They document everything. The procedural violations, the failure to evacuate the pad, the decision to leave the ignition circuit energized while men worked beneath a fully fueled rocket. They even write recommendations: mandatory evacuations, remote defuel systems. All the things that could have saved those 126 lives. And then they classify it, lock it away. The report is never published. The lessons are implemented quietly, in whispers, within the Soviet program only. No other space agency on Earth learns from this disaster. The information that could prevent the next catastrophe remains sealed behind secrecy classifications for nearly 3 decades. The dead can't warn anyone, and the living aren't allowed to. The Soviet space program institutes mandatory 200-meter pad evacuation during all hypergolic fueling operations. Remote defuel systems are developed for subsequent ICBM designs, allowing tanks to be drained without personnel on the pad. Ignition circuits are redesigned with physical interlocks that prevent accidental firing when umbilicals are connected. These changes reduce the risk of similar disasters, but they do not eliminate later accidents. Hypergolic propellants remain inherently dangerous. Leaks, valve failures, and human errors continue to cause injuries and fatalities in the Soviet program throughout the 1960s and 1970s. The procedural reforms help, but the fundamental chemistry does not change. The fuel still ignites on contact. The only safeguard is distance and strict protocol adherence. The disaster remains hidden until 1989. For 30 years, the families of the dead are told only that their relatives died in training accidents. No details. No public memorial. The names are not listed on any monument. Western intelligence agencies suspect a major accident at Baikonur in October 1960, but they have no confirmation. Satellite imagery shows damage to the pad, but the cause and casualties are unknown. The Soviet Union maintains complete silence. Then, in 1989, Mikhail Gorbachev's glasnost policy begins declassifying Cold War secrets. Internal documents are released. Casualty lists are published. Witness accounts appear in Soviet newspapers. Families finally learn what happened. Some receive official death notifications 30 years late. The silence is broken, but the damage is permanent. The suppression of the Netherlands disaster meant that no other space agency learned from the Soviet mistakes. NASA, developing its own Titan II ICBMs with hypergolic propellants, faced similar risks. In 1965, a Titan II exploded in its silo in Arkansas, killing 53 workers during a fueling operation. The causes were similar: a leak during fueling with personnel still in the silo. Had NASA known about Baikonur, evacuation protocols might have been stricter, but the information was locked away. The European Space Agency, developing Ariane rockets with hypergolic upper stages, repeated the same procedural mistakes in the 1970s. The cost of secrecy was measured in preventable deaths across multiple programs. The lessons from Baikonur took decades to propagate worldwide. The exact death toll is still debated. Soviet sources from 1989 list casualty counts ranging from 92 to 165. The conservative consensus is that at least 120 people died on the pad or from injuries in the following days. Marshal Mitrofan Nedelin is among the dead, identified by his medals. Most of the engineers and technicians working at the rocket base died instantly. Some perimeter personnel survived with severe burns and died later in hospitals. The casualty list includes some of the Soviet Union's top rocket engineers, specialists in guidance, propulsion, and fueling systems. The loss of expertise set the R-16 program back by months. But because the disaster was hidden, the full human cost was never publicly acknowledged until 3 decades later. In 1990, the Soviet government authorizes a memorial at Baikonur. A stone monument is erected near Site 41, engraved with the names of the dead. Families are invited to attend the dedication ceremony 30 years after the disaster. Some families decline. The delay feels like a second betrayal. Others attend, seeking closure. The memorial stands today, a quiet marker of a tragedy that was hidden for a generation. Visitors to Baikonur can see the site, but the pad itself was rebuilt and is still in use. The R-16 program continued after the disaster, eventually deploying hundreds of missiles. The disaster did not stop the Cold War arms race. It simply became a footnote, known only to those who survived and the families who waited 3 decades for the truth. This wasn't just another disaster. This was the deadliest space program accident in history. More lives lost in 2 seconds than Challenger, Columbia, and Apollo 1 combined. Yet you've probably never heard of it. Why? Because NASA's tragedies were public. Investigations broadcast worldwide. Lessons shared immediately. But Baikonur? Hidden. The knowledge locked behind Soviet secrecy until the Cold War finally ended. The true cost wasn't just the 120 dead on that pad. It was every preventable accident that followed in other programs. Failures that might have been avoided if the lessons had been shared. The Nedelin disaster proves something crucial. In engineering, secrecy isn't just a political choice. It's a technical failure. And its consequences ripple across decades and borders. The question that haunts the Nedelin disaster is not whether it could have been prevented. It could have. The answer is whether the political culture that caused it has truly changed. Deadline pressure still drives aerospace programs. Political goals still override safety margins. The tools are more sophisticated, the rockets are more reliable, but the human calculus remains the same. When the cost of delay exceeds the perceived risk of proceeding, people make dangerous choices. Nedelin sat in that chair because he believed the cost of missing the deadline was higher than the risk of staying. He was wrong. But the system that forced that choice is still with us. The Nedelin disaster is not just history. It is a warning that repeats whenever pressure and propellant meet on a launch pad. And the calendar matters more than the people standing beneath the rocket.